Hello, welcome back to the Leukopak Lady. Throughout this series, and even in this season, I've talked about variability in manufacturing and clinical outcomes as a major problem in the allogeneic cell therapy field. And it's no secret that I believe a leading cause of this variability is differences in the health status and lifestyle of the healthy donors used for starting material collections. These differences affect the functional fitness of the donor's immune cells, which affects how the cells respond to the manufacturing process and how well they perform within the patient's body to kill targets. Therefore, treating donor and donor material as interchangeable at the start of manufacturing is no longer a good strategy if we want to combat this problem of variability in the field. Donor stratification is a central part of CSM strategy. Donor stratification involves identifying donors based on key ideal biological attributes, matching donors to specific modalities or programs, and using manufacturing and biological data generated by allo developers to guide collection strategy. In some cases, donors whose immune cells demonstrate poor functional fitness will no longer be collected for therapeutic programs. But for those whose cells do demonstrate ideal functional fitness, donor stratification is the part of the CSM strategy that assigns them to the right manufacturing process and therapeutic indication. For example, donors can be stratified based on their percentage or numbers of specific immune cell subpopulations. NK cell-rich donors for NK therapies, T-cell dominant donors for T-cell programs, or donors with elevated rare immune populations like gamma delta T cells or T stem cell memory cells. So some donors may have better resistance to cryopreservation than others, which makes those donor cells better suited for programs that rely on cold chain logistics and centralized manufacturing models. And for reasons not fully understood, some donor cells just perform better in the activities required for successful manufacturing and patient treatment. I've mentioned these activities in recent videos: ability to proliferate, ability to take up a viral vector, and ability to kill target cells like cancerous or autoimmune cells. And there's nothing wrong with donors who have poor performing cells. It simply means their immune cells are not fit for therapeutic use. So without stratification, donor variability goes unchecked in manufacturing processes. When donors with high T cells are collected for an NK therapy, the number of NK cells may not meet the minimum requirement to start the manufacturing run. And when those few donors with high NK cells are collected for a T cell therapy, they aren't being used for NK therapy development. And so this is poor stewardship of the limited donor pool. And when a donor's cells are more susceptible to the stress of cryopreservation are used, it creates frozen products that have low viability upon thaw. And it also demonstrates poor stewardship of the donor pool. And when poor performing cells enter the manufacturing process, they cause a weak or failed run. This makes the manufacturing process less predictable and more variable. It prompts development and manufacturing teams to try and adjust the process to account for biological variability and prevent failures. This costs time and money and results in a suboptimal process overall. And patients receiving poor performing cells as a therapy respond poorly to the treatment. So overall, not stratifying donors makes for suboptimal manufacturing and clinical outcomes, which ultimately affects investor funding and regulatory approvals. On the next episode, I discuss in more detail this phenomenon of cellular sensitivity to the stress of cryopreservation. I'll see you then.